In this video, I'm just going to walk through the starter file for our version of a Sudoku solver. The starter file includes the data definitions we're going to use and a couple simple operations on that data. Now let me stress something really important here. It's totally okay, fine, if when you see these data definitions, you say, I'm not sure I would have come up with those on the first try. I didn't come up with these on the first try. What I did was I came up with some data definitions, and then I started working on the rest of the design, and I realized maybe I could have some data definitions that made things less cumbersome. That's totally okay. Remember, if you're working systematically, what that does is it lets you take advantage of good decisions, and it makes it easy to go back and change bad decisions. So don't worry if you wouldn't have come up with these data definitions. Anyways, now I'm just going to walk through the ones I have to lay the foundation for the rest of the design. So here we go. I'm in Sudoku starter.racket. And the first thing I want to point out is I'm using a require that we've never used before. I'm saying require racket/list, and that's going to get me 3 new primitives that operate on lists that I'll end up using farther down in the starter file. So this is something I definitely didn't put in right away. I didn't know I needed this require until I got down to writing those functions. So here we go. I've got a note at the top that says this is a brute force Sudoku solver. And remember, we used to say that you would just put a one-line description of a program. Here I'm putting a little bit of a textual form of the domain analysis. I just feel the need to say a bit more at the beginning of this file about what's going on. Now, the constants are based on that domain analysis. Val is fairly straightforward. Val is just a natural from 1 to 9. And then I'm saying that a board, I'm going to represent a board as a list. I'm going to represent it as a list 81 elements long. And what I'm saying here is that each element of the list is either a value or false. I could have made a new type here. I would have defined a type called something like entry, which would be one of value or false. But here what I'm doing is I'm doing something a bit more compact. I'm saying just val or false right here. I don't define the separate type. So this is kind of an unnamed type, value or false. And here's the interpretation, which just describes that the board is a 9 by 9 array of squares, where each square has a row and column number, but we're representing it as a single flat list. Now, in a single flat list, there's a position from the 0th element up to the 80th element, 81 elements. And what I'm saying is in that single flat list, the way you convert between a row column and an actual pause, which is an index into the list, is this way. If you've got a pause, if you've got a position, then the row is the quotient of position in 9. In other words, you divide p by 9 and you just take the whole number, and the column is the remainder. And I've got a little function here that goes the other way. It consumes a row and a column, and it produces the position. Okay, so now here's a third thing, which is a unit. And a unit is a list of pause, a list of positions of length 9. So what's this thing? It's the position of every square in the unit. And notice that I haven't been putting example data here. And that's because I've got all my example data down here. So here's a list of all the values, 1 to 9. I've picked this constant b to be false. B stands for blank. Why am I doing that? Well, I'll show you why I'm doing that right now. It makes it much easier for me to write some example data for the boards. So there's board 1. This is the empty board. Every square has false in it. That's why that B is there. It just makes this much more compact than if I had to write false, 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 false. Here's another board. This board has 1, 2, 3, 4 to 9 across the first row. Here's a board that has 1, 2, 3, 4 to 9 in the first column. These are kind of silly boards. And then what I did was I went out on the network and I found some example Sudoku games, right? Remember, the way Sudoku works is you get given a starting board and then you have to finish filling it in. So here's board 4, which I was told was an easy problem. And there's the solution to it. Here's board 5, which I was told was a hard problem, and there's the solution to it. And here's board 6, which some guy named Dr. Arto Inkala says is the hardest one ever. And there's board 6. Here's board 7, which I constructed deliberately to not have a solution. It's very easy to construct a board that doesn't have a solution, but this one, takes a little bit longer to realize it doesn't have a solution. This doesn't have a solution because the only thing that's missing in row 1 is 9. So you'd kind of like to put a 9 there. Except you can't put a 9 there because there's already a 9 in that column. So this board has no solution. So those are some sample boards. Now what I have here is, these are units. Remember that a unit is a list of position of length 9. So this constant rows is a list of units. And look at what it is. There's 9 of them, and each one is the position of each square in the row. So for the first row, the positions of the squares are what? 0, 1, 2, 3, 4, 5, 6, 7, 8. It's simple for rows. Those are the positions. 9 to 17 and so on. But for the columns, for the leftmost column, then the positions of its squares are what? Well, there's 0, 9, 18, 27, and so on. So there's the columns. This is the first column, the second column. You can kind of see here, if you look, the rows go this way. In the columns, it's kind of transposed, right? 0, 1, 2, 3 to 8, 9, 10. If that makes your head hurt, just ignore it. And then for the boxes, let me scroll this just right if I can. There we go. For the boxes, well, the first box is 0, 1, 2, and then 9, 10, 11, and then 18, 19, 20. And here the second box is 3, 4, 5, and then 12, 13, 14, and then 21, 22, 23. So if I take rows and columns and boxes, and I append those together, then I have units. Remember, what these are is they're lists of the positions of the squares in the units. So there's my data definitions and my constants. And I've also provided 2 primitive functions for operating on boards. One is called read square, and it consumes a board and a position, and it produces what's at that position in that board. So if you take read square of board 2, remember what board 2 is, for example. Let's go get it. There's board 2. And using the magic of video editing, what I'll do is I'll bring board 2 down to the bottom here so we can see it for a second. I'll go all the way back down to where we were. So if I say read square in board 2, and then I use that function rc to pause, and so I'm going to read row 0, column 5, then in board 2 we see that that's a 6. And now putting board 3 off to the side for just a second, we see that if I do read square in board 3 of row 7, column 0, that's an 8. So there's read square. And how does read square work? Well, it just needs to go into that list and get the value at that position in the list. Turns out there's a primitive provided by racket/list that does just exactly that, called listRef. So I'm using listRef. And fill square is quite similar to read square, except it takes 3 parameters. It takes a board and a pause, just like read square does. But it also takes a val. And what it does is it produces a new board that's exactly the same as the old board, except at pause, it now has the value val. So this is a way of filling a board in. Read square is a way of seeing what's already in a board. Fill square is a way of writing a number into a board. And here again, I'm using a couple primitives from bracket/list. I'm not going to go into them exactly how take and drop work. That's what this primitive does. Just look at the signature and the purpose and know that that's what fill square does, and the signature and the purpose and know that that's what read square does. I will show you one aside here. Both of these functions consume board and pause, and board and pause are both types that are defined with a one of. So these are what are called functions that consume two one of types. And there is a special part of the design recipe for designing functions like this, having to do with designing two functions that operate on one of data. And these are the ways we would have coded the functions and completed that part of the recipe if we had done it that way. I'm not going to go into that now. Really what I want you to just know for the rest of these Sudoku lectures is these functions, read square and fill square, will do the thing you need them to do. So there you go. That's a summary of the data definitions for Sudoku. And the two primitive functions, read square and fill square, are not quite primitive functions because they're not provided by Racket, but the two functions that I'm giving you to operate on boards. And the key data definitions are val, board, and pause. And then there's some very useful constants. I made these constants, the board constants, my very first time I started writing this. These units constants I didn't make until later. I realized later they would be very useful for me and I made them then. But you have all of them now. Why don't you review this a bit and do the questions in the video right now, and then I'll see you in the next video.